Our entire galaxy is just one brick in a skyscraper spanning billions of light years. We are about to uncover 50 staggering facts about the largest structures in the universe, a journey that will reveal a cosmos far grander and more mysterious than you have ever conceived. You will gain a completely new perspective on your place in the cosmos, moving from our familiar Milky Way to the edge of the observable universe. What cosmic giants, like walls of galaxies so vast they challenge the laws of physics, remain hidden in the darkness? What do you believe is the ultimate fate of these colossal constructions? Human brains simply cannot process the size of these structures. We think of our planet as vast, our sun as immense, but these cosmic giants operate on a scale that redefines the very meaning of big. To even begin to grasp it, we must shrink our own world down to a single grain of sand. On that scale, our entire solar system would be roughly the size of a football field. That alone is a staggering leap, yet the largest structures in the cosmos would not be a stadium or even a city on this scale. They would span the breadth of entire continents. This is the realm of the megaparsec, the unit astronomers use to map the true architecture of the universe. A single megaparsec represents a distance so vast it takes light itself over 3 million years to cross it. These are the fundamental building blocks of our reality, and our journey is only just beginning. This cosmic architecture is built upon a single, magnificent framework known as the cosmic web. It is the largest structure we have ever identified, the true skeleton of the entire observable universe. Picture not a random scattering of stars, but a vast, intricate network of galaxies. These galaxies are not isolated. They gather into immense clusters and superclusters, which themselves form long, winding filaments. These filaments are like the threads of a spider's web, but on a scale so immense they stretch for hundreds of millions of light years. Between these brilliant strands lie the cosmic voids, unimaginably vast and nearly empty deserts of space. This entire structure, this web, did not appear by chance. It was woven from the very fabric of the newborn cosmos. In the first moments after the Big Bang, tiny ripples of density, regions that were ever so slightly more packed with matter than others, were stretched to cosmic proportions by the universe's violent initial growth spurt, a period we call inflation. Gravity then spent billions of years sculpting these ripples, pulling matter into the filaments and nodes we see today, leaving the voids behind. This is not a static picture. It is a dynamic, living structure, and its very existence challenges our understanding of the cosmos. What force could have created those initial seeds, and what strange physics governs the empty voids between the threads of light? These filaments of the cosmic web are not smooth rivers of light. They are dotted with brilliant, dense knots of matter, the universe's greatest metropolitan areas. These are galaxy clusters, the true cosmic cities. A single cluster is a gravitationally bound family of hundreds, sometimes thousands, of individual galaxies, all orbiting a common center of gravity. Our own Milky Way is part of a small group, but a true cluster is a spectacle of cosmic urban sprawl. Yet the galaxies themselves are only the glittering skyscrapers you can see. The real substance of the city lies in what fills the space between them, a sea of superheated gas known as the intracluster medium. This gas is not merely warm. It is roiling at temperatures of millions of degrees, so incredibly hot that it does not shine in visible light, but instead glows with the intense energy of X-rays. In fact, this faint, pervasive glow contains more normal, baryonic matter than all the stars in all the galaxies of the cluster combined. It is the hidden infrastructure that holds the city together. We live on the quiet outskirts of one such metropolis, the Virgo cluster, a collection of over 2,000 galaxies that serves as our local urban center, its gravitational pull gently guiding our own galactic journey. Yet even these brilliant cities of galaxies are not the end of the story. They are merely neighborhoods within a far grander cosmic continent. These are the superclusters, the next colossal rung on the universal ladder. Imagine a sprawling, interconnected archipelago of islands, where each island is an entire galaxy cluster. That is a supercluster. It is a vast collection of clusters, groups, and individual galaxies, all loosely connected by the invisible threads of gravity's tapestry. But here is the crucial, mind-bending detail. Unlike a single galaxy or a dense cluster, a supercluster is not gravitationally bound together. It does not orbit a common center. Instead, this entire immense structure is itself being stretched and pulled by the overall expansion of the universe. It is a temporary pattern in the cosmic flow, a magnificent but fleeting gathering. Our own home, the Milky Way, resides within one such continent known as the Laniakea supercluster. Its name means immeasurable heaven, a title that perfectly captures its staggering scale, encompassing over 100,000 galaxies. This is the hierarchy of our reality, a universe built from structures within structures, each one revealing a new layer of its grand design. But for every brilliant city of light, there is a corresponding cosmic desert of profound emptiness. These are the voids, the vast and lonely regions that stretch between the filaments of the cosmic web. If the web's filaments are the continents of the universe, then these voids are its empty oceans, spanning hundreds of millions of light years with almost nothing inside. They are not perfect vacuums, as a handful of isolated, lonely galaxies might drift through this immense darkness, but their scarcity makes the emptiness all the more absolute. The existence of these voids is not a mere accident. They are a fundamental part of the cosmic architecture, and their sheer size holds a profound secret about the nature of our reality. Because there is so little matter within them, the grip of gravity is exceptionally weak. This allows the mysterious force of dark energy, the engine driving the universe's accelerated expansion, to dominate completely. Within these voids, space itself is stretching faster than anywhere else. They are the primary drivers of the cosmic acceleration we observe, acting as immense, growing bubbles of nothingness that are actively reshaping the entire cosmos. So while we are drawn to the glittering cities of galaxies, the true story of the universe's ultimate fate may be written in these silent, expanding deserts of space. The discovery of a structure of such immense scale was completely unexpected. In 1989, while mapping the positions of galaxies, astronomers stumbled upon a cosmic leviathan. They named it the CF2 Great Wall, a filament of galaxies so colossal it stretched for 500 million light-years in length and 200 million light-years in width. This was not merely a cluster or a supercluster. It was a wall, a continent of galaxies that seemed to defy the very logic of the cosmos. Its identification sent a shockwave through the scientific community. For centuries, a guiding assumption in cosmology had been the cosmological principle, the idea that on the largest scales, the universe is essentially smooth and uniform. Matter, it was thought, would be distributed evenly if you zoomed out far enough. The Great Wall stood in direct contradiction to this. It was proof of profound lumpiness, a glaring irregularity in the cosmic fabric. This single finding shattered old complacencies and ignited a new era of exploration. If a structure this vast could exist, what other giants were lurking in the darkness waiting to be found? The hunt for the universe's true titans had officially begun. The hunt ignited by the Great Wall soon found an even greater prize. In 2003, data from the ambitious Sloan Digital Sky Survey revealed a structure so immense it redefined the upper limits of cosmic architecture. This was the Sloan Great Wall, a filament of galaxies that stretched the concept of size to a breaking point. Its length is a number that loses all meaning without a frame of reference, approximately 1.37 billion light-years. To grasp that, consider a beam of light, the universe's ultimate speedster, racing through the void at over 186,000 miles every single second. That beam of light, starting its journey at one end of the Sloan Great Wall, would spend over 1.3 billion years in the utter darkness of intergalactic space before finally reaching the other side. This single structure is a cosmic road trip that takes light itself an epoch to complete. The existence of such a colossus cements a profound and humbling truth. Our maps of the universe are never finished. With every new survey, with every deeper look into the darkness, we are constantly finding larger structures, each one forcing us to redraw the boundaries of the possible. But the Sloan Great Wall was not the final word. The reigning champion of cosmic structure emerged from a completely different kind of map, one charted by the most violent explosions in the universe. In 2013, astronomers announced the discovery of the Hercules Corona Borealis Great Wall, a structure so colossally vast it strains the very foundations of modern cosmology. This titan was not found by cataloging galaxies, but by pinpointing the locations of gamma-ray bursts. These are the final, catastrophic death cries of massive stars, and they act as brilliant beacons shining across the universe. By mapping where these immense flashes occurred, scientists traced the outline of an agglomeration of matter on a scale previously thought to be impossible. The Hercules Corona Borealis Great Wall is estimated to be an almost unimaginable 10 billion light-years across. Let that number settle for a moment. This single structure spans a significant fraction of the entire observable universe. Its sheer size is the heart of a profound cosmic mystery. According to our fundamental models of cosmology, there is a theoretical maximum size for any structure. This limit is set by the universe's age and the speed of light. Simply put, gravity has not had enough time since the Big Bang to pull matter together over distances larger than about 1.2 billion light-years. The existence of a wall nearly 10 times that size is a glaring anomaly. It stands as a monumental challenge, a silent giant in the darkness that seems to whisper that our understanding of the cosmos, of its infancy and its fundamental rules, is still profoundly incomplete. Our own galactic home is anchored within one of these cosmic continents, the Laniakea supercluster. Its name, drawn from the Hawaiian language, translates to immeasurable heaven, a poetic and fitting title for a structure that contains over 100,000 galaxies, including our own Milky Way. This was not a structure we could simply photograph. Its discovery in 2014 required a completely new way of mapping the cosmos. Astronomers did not just plot where galaxies were, they tracked how they were moving. By meticulously charting the velocities of thousands of galaxies, they revealed a hidden landscape of gravitational flow, a cosmic watershed on an unimaginable scale. All the galaxies within Laniakea, including our own, are drifting like leaves on a slow cosmic river, all flowing toward a common, invisible point of gravitational pull known as the Great Attractor. This mysterious center of mass, hidden behind the dust of our own galaxy's central bulge, acts like a vast gravitational sink, drawing in an entire supercluster of galaxies. So when you look up at the night sky, you are not just looking at stars, you are witnessing a small part of our entire local universe in motion, caught in a gentle but relentless drift toward an unseen, immense heaven. This immense river of galaxies, all flowing toward the Great Attractor, raises a profound question. What exactly is pulling us in? The answer is frustratingly hidden from our direct view, obscured by the thick band of dust and stars at the heart of our own Milky Way. This region is known to astronomers as the zone of avoidance, a cosmic blind spot that blocks our sight of the universe beyond. It is like trying to see a distant city through a dense, permanent fog. Yet we know the Great Attractor is there because we can feel its immense gravitational pull. Our entire galaxy, along with the thousands of others in Laniakea, is racing toward this hidden focal point at a staggering velocity of over 600 kilometers every single second. That is over 2 million kilometers per hour. This unseen concentration of mass is so powerful it can redirect the motion of entire superclusters. For decades, its true nature remained one of astronomy's great puzzles. What could possibly possess enough gravity to command such a vast domain? The mystery only deepened as we peered through the cosmic fog with instruments that could see more than just visible light, revealing that the Great Attractor might not be the final destination, but merely a waypoint on an even grander cosmic journey. The Great Attractor is not the final destination for our galactic river. Our entire Laniakea supercluster, with its 100,000 galaxies, is itself just one branch of a structure so immense it defies simple comprehension. This is the Pisces-Cetus supercluster complex, a true leviathan of the cosmos. Imagine a single filament of the cosmic web, not as a thin thread, but as a colossal river of superclusters, over 1 billion light-years long and 150 million light-years wide. Within this titanic structure, our familiar Laniakea is merely one neighborhood among many. This complex is a gathering of giants, a network of interconnected superclusters that forms one of the largest contiguous structures we have ever identified. Its discovery reveals a profound truth about the universe, a kind of fractal reality where every time we think we have found the largest structure, we zoom out only to find it is part of something even larger. This cosmic nesting doll never seems to end. How many more layers of this immense architecture remain hidden from our current view? And what does this repetitive pattern tell us about the fundamental forces that shaped everything we see? These cosmic bridges are the true threads of the web, long and narrow tendrils of matter weaving the universe together. A galaxy filament is not a solid rope, but a flowing river of dark matter, superheated gas, and thousands of galaxies, all bound by gravity. Their dimensions are what make them so extraordinary. One of these filaments can stretch for hundreds of millions of light-years across the void, a distance so vast it could connect entire superclusters. Yet its width is a mere 20 to 30 million light-years, a cosmic thread so slender compared to its length. Imagine a single strand of spider silk, but one that stretches from the Earth to the Sun and back again over 1,000 times, yet is no wider than a garden hose. That is the impossible, needle-like proportion of these universal bridges. They are not just passive strings of light, but dynamic highways. Along these filaments, galaxies are funneled like cars on a freeway, flowing steadily from the empty deserts of the voids toward the brilliant, crowded intersections where clusters form. This is the hidden traffic of the cosmos, a slow but relentless migration guided by the invisible architecture of dark matter, shaping the distribution of everything we can see. But these flowing rivers of galaxies and the voids between them are not held together by the matter we can see. The brilliant cities of light are merely the glittering decorations on a framework built from something far more mysterious. The true architect of the cosmic web is dark matter. This invisible substance is the most crucial component of every large structure in the universe. We know it exists not because we can see it, but because we can feel its immense gravitational pull. Think of it like this. If the cosmic web were a magnificent city at night, the glowing galaxies would be the streetlights and the lit-up buildings. But dark matter is the underlying grid of streets, the foundations, and the very land upon which the entire city is built. The normal matter, the stars and gas that we see and are made of, simply follows the gravitational blueprint laid down by this unseen dark matter. It flows into the gravitational wells that dark matter creates, pooling there to form galaxies and clusters. Without this mysterious substance, which makes up about 27% of the universe, gravity would not have been strong enough to pull matter together over such vast distances. The primordial soup of the early universe would have remained just that, a thin, uniform haze. There would be no great walls, no filaments, no clusters. The cosmos would be a dark and lonely place, devoid of the grand structures that give it form and beauty. Yet this entire cosmic architecture, from the smallest filament to the largest wall, exists within a fundamental prison of perception. We are bound by the Hubble volume, the ultimate sphere of the knowable. This is not a physical boundary in space, but a limit in time. It defines the spherical region of the universe from which light has had enough time, across the entire age of the cosmos, to finally reach our telescopes. Every star, every galaxy, every great wall we have ever seen or ever will see resides within this bubble. Think of it as a cosmic event horizon in reverse, marking not the edge of a black hole, but the edge of our vision. We cannot see anything beyond it, not because it is not there, but because the light from those distant realms has not had enough time to get here. The universe beyond our Hubble volume is forever hidden from us, its light still racing through the void, destined to never arrive. This creates a profound implication for the titanic structures we have discovered. When we gaze upon a wall like Hercules' corona borealis, stretching 10 billion light-years, we are not necessarily seeing the entire structure. We are only seeing the part of it that falls within our observable bubble. The rest of that cosmic leviathan, its true and full form, could extend far beyond our horizon into the unknowable darkness. The largest things in existence might be even larger than we can possibly conceive, their complete shapes lost to us forever. This theoretical boundary is known as the end of greatness. It is a cornerstone of modern cosmology, the predicted scale where the universe finally becomes smooth. If you zoom out far enough, the thinking goes, the lumpiness of the cosmic web should dissolve into a uniform, featureless sea of galaxies. The grand structures, the walls and the voids, should simply vanish from the map, proving the universe is fundamentally homogeneous. This principle is not just an abstract idea. It is baked into our most fundamental models of how the cosmos works. Yet the discovery of titans like the Hercules corona borealis Great Wall throws this entire concept into question. This wall is not just large, it exists on a scale far beyond the predicted limit of homogeneity. It is a colossal lump in a cosmic soup that was supposed to be smooth. How can such a structure exist if the universe is meant to become uniform at a smaller scale? This is not a minor discrepancy. It is a direct challenge, a cosmic anomaly that forces astronomers to reconsider some of their most basic assumptions. Perhaps our understanding of the initial conditions of the universe is incomplete, or maybe the mysterious force of dark energy plays a more complex role in structuring the cosmos than we ever imagined. The end of greatness may not be an end at all, but merely a horizon in our current understanding, a limit we have not yet managed to cross. The blueprint for the cosmic web was not drawn by chance. Its design was etched into the fabric of the cosmos in the first 400,000 years of its existence, a time when the universe was not transparent, but a searing, opaque fog of plasma and light. In that primordial fire, physics itself was writing the rules. Ordinary matter, the baryons that would one day form stars and planets, was trapped in a cosmic tug-of-war. On one side was the immense outward pressure of radiation, the blinding light that filled every point in space. On the other was the relentless inward pull of gravity, trying to clump matter together. This conflict created sound waves, not sound as we know it, but colossal spherical pressure waves that rippled outward through the hot soup at over half the speed of light. Imagine dropping a stone into a pond, but a pond where the ripples expand at nearly the ultimate speed limit of the universe. These are the baryon acoustic oscillations. For nearly 400,000 years, these waves expanded, pushing matter outward in a growing shell. Then, in a single transformative moment, the universe cooled enough for atoms to form. The fog lifted, the plasma cleared, the universe became transparent, and in that instant the waves were frozen in place. The ripples stopped propagating, leaving behind a permanent, spherical imprint in the distribution of matter. This is the fundamental unit of cosmic construction. The distance those waves traveled before they froze became a preferred scale, a standard size for how matter would begin to clump. Today, we can still see this ancient echo, When astronomers map the positions of millions of galaxies, they find a subtle but undeniable statistical preference for galaxies to be separated by a specific distance, a distance that corresponds to the size of that frozen sound wave. This fossilized ripple, now stretched to nearly 500 million light-years across by the expansion of the universe, acts as a cosmic ruler. By measuring this standard length in the sky, we can chart the expansion history of the cosmos itself, tracing our way back to the very first vibrations that set the stage for everything that was to come. That frozen ripple in the distribution of galaxies has a direct origin, a single snapshot from the universe's infancy. We can still see the moment those sound waves were captured, in the oldest light that fills all of space. This is the cosmic microwave background, the universe's very first photograph, taken when it was a mere 400,000 years old. It is not a picture of galaxies or stars, but of a hot, dense fog of plasma cooling just enough for atoms to form, releasing the light that had been trapped within. Today, that brilliant flash has cooled and stretched into a faint microwave glow that permeates every cubic inch of the cosmos, a cold relic of a fiery birth. If your eyes could see microwaves, the entire night sky would not be black, but would glow with a uniform, dull light. But this glow is not perfectly uniform. When scientists map it with incredible precision, they find a tapestry of minuscule temperature differences, tiny fluctuations where some patches are just a few millionths of a degree warmer or cooler than the average. These subtle variations are everything. Each slightly warmer spot on this baby picture corresponds to a region of the primordial universe that was ever so slightly denser, packed with just a little more matter. These were the gravitational seeds planted in the fabric of space-time. Over the ensuing billions of years, gravity got to work. It amplified these tiny imperfections, relentlessly pulling more and more matter toward these dense spots. The warm spots in that ancient light grew into the first stars, then galaxies, then the immense clusters and the sprawling filaments of the cosmic web. The entire grand architecture of the modern universe, every great wall and every vast void, was encoded in that subtle pattern of hot and cold, a blueprint written in the faintest whisper of heat from the dawn of time. That ancient blueprint, frozen into the cosmic microwave background, did not remain a passive pattern for long. Gravity began its patient work, and we can actually witness the construction process by looking back in time. Billions of light-years away, we find the universe's construction sites, infant cities known as protoclusters. These are not the brilliant, mature galaxy clusters of today, but their primordial ancestors. We see them as they were when the universe was only a fraction of its current age, vast and dense regions of raw hydrogen gas and some of the very first galaxies just beginning to coalesce. They appear to us not as a single, concentrated city, but as a sprawling, chaotic suburb where dozens of young, energetic galaxies are being drawn together by gravity's invisible hand. Observing these protoclusters is like finding a photograph of a bustling modern metropolis when it was still a collection of small frontier towns. We are watching the cosmic web assemble itself in real time, or rather, in the light that has traveled for billions of years to reach our telescopes. By studying these infant cities, we can trace the entire life story of a galaxy cluster, from its first gravitational whispers to the immense cosmic metropolis it will one day become. What forces determine which of these young galaxies will become the dominant central giants, and which will remain smaller satellites forever orbiting a brighter neighbor? But the universe's grand design reserves its most profound silences for the emptiest places of all. In the northern constellation of Boötes, the herdsman, lies a sphere of nothingness so vast it has become legendary. This is the Boötes Void, a cosmic desert of staggering proportions. Imagine a perfect sphere of space roughly 330 million light-years across. Within a volume that large, you would normally expect to find thousands, perhaps even tens of thousands of brilliant galaxies. Yet when astronomers peer into this region, they find a haunting emptiness. Only about 60 galaxies have been catalogued within its immense borders. To put that into perspective, if the cosmos were a city, the Boötes void would be a central park the size of a continent, containing only a handful of lonely streetlights. The scarcity is so extreme that if our own Milky Way were placed at the void's center, we would not have known other galaxies existed until the 1960s. The sheer scale of this nothingness challenges our understanding of how matter is distributed. How did such a colossal pocket of emptiness come to be? One leading theory suggests it is not a single void, but a cosmic accident where several smaller voids have merged together over billions of years, like soap bubbles coalescing into one gigantic cavity. Yet its near-perfect spherical shape is puzzling, prompting more exotic ideas. Could it be the imprint of an unimaginably vast cosmic collision in the earliest moments of time, or perhaps the signature of a type of physics we have not yet discovered? The Boötes void stands as a monument to the fact that in the cosmos, the absence of something can be just as compelling and mysterious as its presence. This cosmic emptiness is not just a distant curiosity, it might be our own home. A controversial but fascinating proposal suggests that we, the Milky Way, are living inside a void. Astronomers Keenan, Barger, and Cowie presented evidence that our galactic neighborhood sits within a vast underdensity of matter, now called the KBC void. This is not a perfect emptiness like the Boötes void, but a relative desert, a bubble in the cosmic web roughly 2 billion light-years across. Within this immense region, the density of galaxies, clusters, and all forms of matter is significantly lower than the cosmic average. We are not at the center of the universe, but we may very well be at the center of a colossal pocket of nothing. This idea is more than just a cosmic oddity. It has profound implications for one of the most critical numbers in all of cosmology, the Hubble constant. This constant measures the current rate of the universe's expansion. For decades, astronomers have faced a growing crisis. Measurements of the Hubble constant taken from the nearby universe, using methods like supernova, disagree with the value predicted from the pristine early universe as seen in the cosmic microwave background. The numbers do not match, and the KBC void offers a potential explanation. If we are living in a local underdensity, then the gravitational landscape around us is unusual. There is simply less matter nearby to pull back and slow down the expansion through its gravity. This means that in our local void, space would be stretching faster than it is in the denser, average regions of the cosmos. Our measurements of the expansion rate would therefore be skewed, showing a value that is artificially high. We would be mistaking our local emptiness for a global property of the entire universe. The void would be a cosmic hall of mirrors, distorting our perception of reality itself. If this is true, it forces a humbling realization. Our entire view of the cosmos, the foundation upon which we build our models, might be fundamentally biased by our unremarkable address inside a billion light-year bubble. Far out in the cosmic dark, 7 billion years away, a titan is colliding. This is ACTCLJ 01024915, a galaxy cluster so immense and violent it earned the nickname El Gordo, the Fat One. It is not merely a city of galaxies, it is a metropolis in the throes of a catastrophic, slow-motion train wreck. El Gordo is actually two enormous subclusters, each a family of hundreds of galaxies, smashing into one another at millions of miles per hour. The energy released by this collision is beyond human comprehension. The sea of superheated gas between the galaxies, the intracluster medium, has been compressed and heated to a staggering 200 million degrees, making El Gordo one of the hottest and most luminous X-ray sources ever discovered. If your eyes could see X-rays, this single cluster would outshine the full moon in our sky. But the visible fireworks, the brilliant galaxies themselves, are not the main event. They are like bits of flotsam tossed on the surface of a raging ocean, largely passing by one another unscathed in the vast emptiness between stars. the real story of this cosmic collision is told by the things we cannot see. When astronomers mapped El Gordo, they found a profound mystery. The most intense glow of X-rays, marking the bulk of the colliding gas, was separated from the concentrations of mass which were located by their gravitational lensing effect. This separation reveals the ghost in the machine, dark matter. The colliding clouds of normal gas slammed into each other and slowed down, but the dark matter, which does not interact with anything except through gravity, simply sailed right through the crash. This bizarre behavior, where the invisible skeleton of the cluster becomes detached from its glowing, hot gas, is some of the most compelling evidence we have for the existence and nature of dark matter. El Gordo is a cosmic particle accelerator on the grandest possible scale, a unique laboratory showing us how the fundamental components of our universe behave under the most extreme conditions imaginable. Closer to home, a mere 320 million light-years away, rests the Coma Cluster, a perfect sphere of 1,000 galaxies. This is not a sprawling, filamentary supercluster, but a dense, spherical city, one of the richest and most studied clusters in our entire sky. Its core is dominated by two colossal elliptical galaxies, NGC 4874 and NGC 4889. Each one a titan containing trillions of stars. They are the twin suns around which this entire galactic metropolis orbits. For astronomers, the Coma Cluster is a classic textbook example, a laboratory for understanding how these immense structures work. Yet in the 1930s, this familiar cluster revealed a deeply unfamiliar truth. When Swiss astronomer Fritz Zwicky measured the velocities of galaxies swirling within the cluster, he found something deeply unsettling. They were moving far, far too quickly. According to the laws of gravity, the combined gravitational pull from all the stars and gas we could see was utterly insufficient to hold the cluster together. At the speeds they were traveling, those galaxies should have flown apart long ago, scattering into the cosmic void. The only possible explanation was that there had to be something else present, a huge amount of invisible matter providing the extra gravitational glue to keep the city from tearing itself to pieces. Zwicky called this missing substance Dunkel Materie, dark matter. This single observation in a nearby cluster was the first major clue that the universe we see is only a tiny fraction of the universe that actually exists. The brilliant pinwheels of 1,000 galaxies were just the visible evidence of a much deeper, hidden reality holding everything together. Even the grandest cosmic continents are temporary. The same expansion of space that creates the great voids is also unraveling the connections between the galaxies within a supercluster. Unlike a true galaxy cluster, which is a gravitationally bound family held together by its own immense mass, a supercluster is a fleeting pattern. It is a magnificent but loose collection of galaxies, groups, and clusters that share a common drift through the cosmos, but not a permanent bond. Gravity is too weak across such immense distances to permanently tie this entire structure together. Think of it as a massive school of fish all swimming in the same current. They appear as a single, coordinated entity from a distance, but there is no physical tether holding them together. A change in the current, a shift in the flow, and the school can easily disperse. This is the fate of every supercluster, including our own Laniakea. Over billions of years, the relentless expansion of the universe will act like a strengthening current, stretching the space between its member galaxies. The delicate filaments that connect the clusters within it will thin and eventually snap. The galaxies that now flow together toward the great attractor will one day find their paths diverging, pulled apart by the overall stretching of the cosmic fabric. This reveals a universe that is not a static sculpture, but a dynamic and evolving masterpiece, where even the largest structures are subject to the relentless flow of time and space. Our most immediate cosmic neighborhood is a single, flattened plane of galaxies known as the local sheet. This is the specific galactic street we live on, a structure that pins our Milky Way and all its closest neighbors into a remarkably flat arrangement. Think of the Grand Laniakea supercluster as an entire continent, and the local sheet is our quiet, suburban county within it. This plane is home to every galaxy whose motion is directly influenced by our own. It includes the Great Spiral of Andromeda, our closest major galactic neighbor, the smaller Triangulum galaxy, and roughly 50 other smaller, dwarf galaxies all orbiting within this common disk. We are not floating in isolation. Our entire local group is embedded within this sheet, which acts like a fundamental plane of reference for our corner of the universe. This structure gives us our most precise cosmic address, a specific location within the unimaginable vastness of the Virgo supercluster and the Laniakea flow. It is a humbling reminder that even on the scale of superclusters, our universe has a distinct grain, a local geometry that dictates the paths of the galaxies we know best. Our cosmic address has been rewritten. Before the discovery of the Laniakea supercluster, our galactic home was classified within the Virgo supercluster. This older map centered everything on the immense gravity of the Virgo cluster, a brilliant gathering of over 2,000 galaxies. It was a logical way to group the galaxies around us based primarily on their location, as if drawing a circle on a map and saying everything inside it belongs to the same country. But science is a living process, a constant refinement of our understanding with better tools and deeper insights. The key shift came when astronomers realized that location alone is not enough to define a true supercluster. Two galaxies might be neighbors in space, yet be on completely different cosmic trajectories, pulled by separate gravitational currents. The new map of Laniakea did not just look at where we are. It listened to how we are moving. By charting the subtle velocities of thousands of galaxies, it revealed the underlying watershed of our local universe. This showed that our old home, the Virgo supercluster, is actually just a part of Laniakea's immense structure, one dense region within a much larger river of flow. The universe did not change, our perception of it did, evolving from a simple snapshot into a dynamic movie that reveals our true place in the immeasurable heaven. Beyond our local flow toward the great attractor lies an even greater gravitational anchor. The Shapley concentration is the single most massive gathering of matter we have ever mapped in our cosmic neighborhood. This is not merely a supercluster, but a dense knot where several superclusters have themselves converged. A staggering collection of galaxies located roughly 650 million light-years from Earth. Its gravitational influence is so profound that it actively tugs on our entire local group of galaxies. While the Great Attractor acts as our immediate destination, the Shapley concentration is the deeper current in the cosmic river, a primary force contributing to our peculiar motion through the universe. We are not just falling toward a single point, but are caught in a complex web of gravitational pulls from multiple titans, with Shapley's immense mass ensuring our journey is anything but a straight line. This reveals a universe where gravity's reach is truly intercontinental, where a mass concentration 500 million light-years away can still make its presence felt, gently guiding the path of our own galactic home. Yet the cosmic web is not the only pattern we find written in the heavens. Another class of titan emerges from the universe's most brilliant beacons. These are the large quasar groups, immense gatherings of the universe's most luminous objects. Quasars are not stars, but the ferociously active cores of distant galaxies, powered by supermassive black holes feasting on vast amounts of gas and dust. They shine with the light of 1 trillion suns, visible across the deepest reaches of space. When astronomers began to map their positions, they found that these brilliant pinpricks of light were not scattered randomly. They too trace out immense structures clustering together in groups that defy comprehension. The most famous of these, discovered in 2012, is known simply as the Huge Large Quasar Group. Its scale is almost a parody of size, a structure measuring roughly 4 billion light-years in its longest dimension. To put that into perspective, this single cluster of quasars is so large it could contain dozens of structures the size of the Sloan Great Wall. Its existence sends another seismic shock through the foundations of cosmology. The cosmological principle, the idea that the universe should look roughly the same in every direction when viewed on a large enough scale, predicts a maximum size for any structure of about 1.2 billion light-years. The huge large quasar group is more than 3 times that limit. How could gravity have possibly assembled such a colossal grouping of these hyperluminous objects in the time available since the Big Bang? The sheer number of quasars clustered together in one region suggests a fundamental lumpiness in the early universe far greater than our models allow. Each of these brilliant beacons is a clue, a point of light marking a node of immense ancient energy, and together they draw a pattern on the sky that our current understanding of physics struggles to explain. And just when we thought the map was settled, a new challenger appears on the edge of our vision. In 2021, a doctoral student named Alexia Lopez was analyzing the light of distant quasars when she noticed something impossible. Stretching across a colossal 9.3 billion light-years of space, she found a near-perfect symmetrical curve of dozens of galaxies. This is the giant arc, a structure so vast it covers an entire 15th of the observable universe. Its scale is one thing, but its form is the true shock. It is not a random clump or a vague wall. It is a distinct crescent-shaped filament, a graceful arch spanning 3.3 billion light-years from tip to tip. The probability of such a symmetrical, coherent structure forming by random chance under our standard model of cosmology is vanishingly small. It is a statistical anomaly so severe it screams that something is wrong with our fundamental picture. This is not just another large thing, it is a question mark written in galaxies across the sky, a direct challenge to the cosmological principle itself. If the universe is supposed to be smooth and featureless on the largest scales, how can it possibly contain a recognizable, symmetrical shape that is almost a tenth of its total size? The giant arc forces a profound and uncomfortable choice. Either we have witnessed a 1 in a million cosmic fluke, a statistical miracle that just happens to exist in our line of sight, or our understanding of the universe's fundamental homogeneity is fundamentally flawed. This single arc of light could be the thread that unravels our entire cosmological model, demanding a physics we have not yet dreamed of. Even the deepest cosmic deserts are not completely barren. While the voids between the great filaments appear as vast, empty spheres on our maps, they are not perfect vacuums. These regions are simply the universe's most sparsely populated neighborhoods, home to a diffuse and lonely collection of matter. Drifting through this immense darkness are isolated galaxies, often referred to as field galaxies. These are the cosmic hermits, islands that have evolved in profound solitude, cut off from the bustling traffic and gravitational interactions that shape galaxies in the crowded clusters. Without neighbors to merge with or strip their gas away, these lonely galaxies have lived unique and quiet lives, often forming stars at their own undisturbed pace. But the galaxies are just the most visible residents. The voids are also filled with an incredibly tenuous fog of ionized gas, spread so thin it is almost imperceptible. And like every other part of the cosmos, they are permeated by the invisible presence of dark matter, though its density here is far lower than in the dense filaments. This faint, universal substrate means that a void is not a hole in the universe, but rather a region where the cosmic web exists in its most stretched and diluted form. The grand architecture is still there, just faded to an almost silent whisper. This accelerating emptiness is actively reshaping the entire cosmic architecture. Because voids contain so little matter, their gravitational pull is exceptionally weak. There is simply not enough mass inside them to hold their own borders together against the relentless push of dark energy. This creates a runaway effect. As a void expands, it becomes even emptier, which further weakens its gravity, allowing it to expand even faster. The result is a differential expansion where these cosmic deserts are stretching at a rate that outpaces the universe's average. They are the fastest growing regions in the entire cosmos. This isn't a passive process, it acts like a cosmic broom. The void's accelerating edge pushes against the sparse matter and lonely galaxies within it, herding them outward. This gentle but relentless pressure sweeps material out of the emptiness and funnels it directly into the surrounding filaments and walls of the cosmic web. Think of it like water being squeezed from a sponge. The voids are contracting in terms of their matter content, even as they grow physically larger. This process continuously feeds the great structures, making the dense regions of the web even denser over billions of years. The brilliant cities of galaxies grow brighter and more massive, not just from their own gravity, but because the expanding deserts around them are constantly evicting matter and sending it their way. The universe is not merely expanding, it is actively organizing itself, with the emptiest places doing the heavy lifting to build the greatest structures of all. This intricate cosmic architecture was not revealed by a single photograph, but pieced together through a monumental effort of cosmic cartography. The key to unlocking the three-dimensional structure of the universe lies in a simple but profound property of light known as redshift. As the universe expands, it stretches the very fabric of space, and this stretching also extends to the light waves traveling through it. The light from distant galaxies is shifted towards the red end of the spectrum, much like the sound of a receding ambulance siren drops in pitch. The farther away a galaxy is, the faster it appears to be receding from us, and the more its light is redshifted. By carefully measuring this redshift for millions of galaxies, astronomers can calculate their distances from Earth. This transforms the night sky from a flat tapestry of dots into a deep, three-dimensional map. It is the ultimate tool for cosmic archaeology, allowing us to excavate the universe layer by layer. This monumental task required a new kind of telescope, one designed not for pretty pictures but for pure data. Projects like the 2-degree field Galaxy Redshift Survey, or 2DF, pioneered this effort in the 1990s, using a custom-built plate with 400 optical fibers to capture the light of hundreds of galaxies at once. This was followed by the Sloan Digital Sky Survey, which began creating an unprecedented map of the cosmos, cataloging the positions and redshifts of over 1 million galaxies. The latest in this lineage, the Dark Energy Spectroscopic Instrument, or DESI, is currently undertaking the most ambitious survey yet. It uses 5,000 tiny robotic motors to position individual fibers with hair's breadth precision, each one targeting a single, distant galaxy. Night after night, it gathers the faint light from these island universes, measuring their redshifts and plotting their positions in an ever-growing virtual cosmos. These surveys have given us the data points to connect, revealing the grand filaments, the vast walls, and the immense voids in breathtaking detail. The cosmic web did not appear in a flash of inspiration, but was patiently woven from millions of individual points of light, each one a story, each one a data point in the greatest map ever made. These grand maps of the cosmos are not just observations, they are predictions put to the ultimate test. To truly understand how the cosmic web grew from a faint whisper in the microwave background to the sprawling architecture we see today, we must build our own universes. This is the realm of supercomputer simulations, digital laboratories where the entire history of the cosmos is played out from the first moments to the present day. The most famous of these, like the Millennium Simulation and the more recent Illustris TNG project, begin with a simple but profound starting point. They take the exact initial conditions imprinted on the cosmic microwave background, that baby picture of the universe, and populate a virtual space with billions of particles representing dark matter, gas, and the laws of physics as we know them. They program in the rules of gravity, the dynamics of dark energy, and the complex behavior of collapsing gas clouds that form stars and galaxies. Then they press play. Over months of computation, these simulations fast-forward through 13.8 billion years of cosmic evolution, and the result is nothing short of breathtaking. From that smooth, primordial soup, a familiar pattern emerges. The dark matter weaves itself into a vast, cosmic spiderweb of filaments. The normal matter follows this invisible blueprint, flowing into the strands and nodes to form brilliant galaxies. Vast voids open up between the luminous threads. The simulations do not just produce a vague resemblance, they generate a universe that looks statistically identical to the one we observe through our telescopes. This successful replication is one of the strongest validations we have for our entire cosmological model. It tells us that our understanding of dark matter's gravitational role and the expansive push of dark energy is essentially correct. The fact that we can start with the universe's first cry and end with a perfect digital twin of the cosmic web means we are truly deciphering the fundamental laws that built everything. That faint cosmic microwave background glow is more than just a baby picture. It is also a universal backlight illuminating the structures in front of it. As this ancient light travels for billions of years to reach us, it must pass through the vast seas of superheated gas that fill galaxy clusters. When a microwave photon from the primordial fire enters this hot gas, it can collide with a high-energy electron. The photon gets a kick of energy, a boost that pushes it from the microwave part of the spectrum into higher energy wavelengths. This is the Sunyaev-Zeldovich effect, a subtle but powerful distortion in the cosmic background radiation. For the clusters themselves, it is like being caught in a cosmic spotlight, casting a specific and recognizable shadow against the brightest wall in the universe. By scanning the sky for these telltale shadows, astronomers can find the most massive clusters with incredible efficiency. This technique is not limited by distance in the same way that optical light is. It allows us to detect these immense cities of galaxies even at the very edge of the observable universe, pinpointing the densest nodes of the cosmic web across the vastness of space and time. This method has become a cornerstone of modern cosmology, providing an independent census of the universe's largest gravitationally bound structures and helping to trace the invisible skeleton of dark matter that holds them all together. But to truly weigh these cosmic giants, we need a scale that can measure the invisible. The universe provides one through a phenomenon so strange it seems like magic: gravitational lensing. The core idea comes from Einstein's theory of general relativity, which tells us that mass warps the fabric of space and time. A massive object like a galaxy cluster acts like a lens in space, bending the path of any light that passes near it. So when we look at a distant galaxy located directly behind a massive foreground cluster, its light is distorted as it travels through this warped space. The result is not a single clear image of the background galaxy, but often multiple stretched and smeared copies of it, forming brilliant arcs of light that curve around the cluster's core. These are not real physical structures, but cosmic mirages, ghostly images sculpted by gravity. By meticulously studying the exact shape and degree of this distortion, astronomers can perform a remarkable feat. They can calculate the total amount of mass in the foreground cluster that caused the bending. This measurement is crucial because it accounts for everything: the glowing galaxies, the hot X-ray gas, and most importantly, the vast halo of invisible dark matter that makes up the bulk of the cluster's weight. Gravitational lensing is the only tool we have that allows us to literally see the gravitational influence of dark matter directly. It reveals the hidden skeleton of the cosmic web, mapping the distribution of mass along the vast filaments and within the colossal voids, painting a picture of the universe not as it appears, but as it truly is, a structure built predominantly from shadow. The grand cosmic web, with all its threads and cities of light, is not a permanent cathedral. It is a sandcastle on the shore, and the tide of dark energy is coming in. In the far future, if this mysterious force continues to accelerate the universe's expansion unchecked, the fate of this magnificent architecture is one of utter dissolution. The unraveling will be a slow, methodical process, starting with the largest connections. The delicate filaments that bind superclusters together, those rivers of galaxies already stretched thin by cosmic flows, will be the first to snap. The great walls and continents will drift apart, their gravitational bonds severed forever by the relentless stretching of space. Each supercluster will become an isolated island universe, adrift in an ever-widening sea of nothingness. But the decay will not stop there. As the expansion accelerates further, it will begin to attack structures we consider fundamental. The immense gravity that holds a galaxy cluster together, powerful enough to bind 1,000 galaxies, will be overcome. These brilliant cities will be pulled apart, their member galaxies scattered into the void like dandelion seeds in a hurricane. The isolation will become absolute. Our own local group of galaxies, bound by the mutual gravity of the Milky Way and Andromeda, may hold out for a time, but it too is not immune. Eventually, the stellar fabric of individual galaxies will be shredded. Solar systems will be torn from their galactic moorings. In a final, terrifying epoch known as the Big Rip, the very fabric of spacetime itself could tear apart. Planets would be ripped from their stars, and atoms would be pulled asunder, leaving a cold, dark, and utterly lonely cosmos where the universe's grandest architecture is nothing but a forgotten memory. Long before the great walls and clusters existed, the cosmic web was already hard at work. Its filaments, woven from dark matter, served as the universe's first and most vital delivery system. In that primordial era, over 13 billion years ago, these strands were not dotted with brilliant cities of galaxies. They were dark rivers of pure hydrogen and helium gas flowing along the invisible gravitational channels. Where these rivers intersected, where the flows of gas collided and pooled, the first protogalaxies were born. It was a slow, majestic gathering. Gravity patiently drew the cold, pristine gas into ever denser knots within the filaments. These knots grew massive enough to begin collapsing under their own weight, triggering the first furious bursts of star formation. The darkness of the early cosmos was punctured not by random, isolated points of light, but by brilliant beads on a string. Each new galaxy ignited along the luminous threads of the web, tracing its structure in fire. This was not a chaotic explosion of light, but a deliberate unveiling, a grand design switching on section by section. The very first galaxies were therefore never truly alone. They were connected from birth by the flowing currents of gas that gave them life, their positions dictated by a blueprint written into the fabric of reality itself. But the cosmos holds a deeper current, a motion that defies all local explanation. Astronomers have detected a phenomenon known as the dark flow, a mysterious and coherent drift of entire galaxy clusters on a scale so immense it challenges the very definition of our reality. The story begins with galaxy clusters, the universe's greatest cities, and the hot gas that fills the spaces between their galaxies. As the ancient light from the cosmic microwave background passes through this gas, it gets a subtle energy boost, a fingerprint known as the Sunyaev-Zeldovich effect. When scientists meticulously mapped this effect for over 1,000 clusters, they found something deeply unsettling. The clusters were not just moving with the general expansion of the universe. They were all streaming in the same direction, like leaves caught in a vast, invisible river. This motion was coherent across billions of light years, a coordinated drift that should be impossible. According to our standard models, the gravitational pulls from all the known structures within our observable universe, from the Great Attractor to the Shapley concentration, should cancel each other out on such enormous scales. There should be no preferred direction for this flow, yet the data suggests there is. The only plausible explanation is as breathtaking as it is controversial. This dark flow may be caused by the gravitational tug of something unimaginably vast that lies beyond our cosmic horizon, outside the bubble of our observable universe. A structure so colossal that its gravity reaches across the void, pulling on everything we can see. This is not just a mystery, it is a potential window into the cosmos beyond our view, a hint that our universe is part of a far grander, perhaps infinite, reality whose true architecture remains hidden in the darkness. The Boss Great Wall proves that our cosmic maps still hold colossal secrets. Discovered in 2016 using data from the Baryon Oscillation Spectroscopic Survey, this structure is a sprawling complex of superclusters, a wall within walls that stretches for over 1 billion light-years. Its identification so recently underscores a humbling truth. Even with our most advanced digital sky surveys and powerful supercomputers, we are still finding giants hiding in plain sight, their immense scale only becoming clear when we step back to look at the entire picture. Think of it like this: for centuries, humanity mapped the coastlines of continents, believing we had charted every major landmass. Then one day, we finally developed satellites, looked down, and realized that several of those coastlines were actually connected, forming a single, gargantuan island we had never perceived. The Boss Great Wall is that kind of discovery. It is not a single, neat filament, but a dense and tangled knot in the cosmic web, a metropolitan region on a scale that defies belief. Its existence confirms that our census of the universe's largest structures is nowhere near complete. What other leviathans are waiting, their full forms still obscured by the limitations of our current vision, or by the simple fact that they are so immense we are still living inside them? These vast cosmic continents are not all shaped the same. Far from being simple spheres or blobs, superclusters can take on wildly unique and intricate forms that reflect the chaotic and complex history of their birth. Consider the Saraswati supercluster, a truly ancient leviathan discovered lurking over 4 billion light-years away. This is not a mere gathering of galaxies, but a sprawling, chain-like structure, a celestial necklace strung with dozens of massive clusters. Its shape suggests a history of dramatic mergers, where smaller filaments and groups have woven themselves together over billions of years, creating a tangled web of cosmic proportions. Then there is the Horologium Reticulum supercluster, a name that translates to the clock and the net. It is an almost perfectly elongated concentration of galaxies, a colossal river of light stretching across the southern sky. Its slender, linear form makes it one of the most massive and distinctly shaped structures in our entire observable universe. These peculiar architectures are not random flukes. They are frozen records of the initial conditions of the universe, the specific pattern of density ripples that existed in that primordial fire. Gravity then amplified those specific patterns, pulling matter into these unique and varied shapes over cosmic time. The fact that we see such a stunning variety tells us that the process of building the universe was not a neat and orderly assembly, but a messy, dynamic, and deeply creative act of construction. This same principle of light losing energy as it climbs from a cosmic pit connects one of the universe's largest structures to one of its oldest and most puzzling mysteries. Deep within the cosmic microwave background, that baby picture of the universe, lies an anomaly astronomers call the cold spot. It is not a tiny imperfection, but a sprawling region of the sky that is significantly colder than the average glow. For years, its existence was a profound enigma. How could a patch of the primordial universe be so different from its surroundings? One compelling solution points a finger at a colossal emptiness lying between us and that ancient light. This is the Eridanus supervoid, a vast spherical desert of space nearly 2 billion light-years across. As the ancient photons of the CMB traveled toward us, their journey took them directly through this immense void. Think of a ball rolling up a steep hill. As it climbs, it loses energy and slows down. Now replace the ball with a particle of light and the hill with the gravitational landscape of the supervoid. A void, being a region of extremely low density, has a weaker gravitational pull than the surrounding universe. It is like a shallow well in the fabric of space-time. When the CMB light entered the void, it was not affected much, but as it exited, it had to climb out of this gravitational well. That climb cost the light energy. For a photon, losing energy means its wavelength stretches, shifting it toward the cooler, redder end of the spectrum. This effect, known as the integrated Sachs-Wolf effect, is subtle, but across a void as immense as Eridanus, the energy loss adds up, creating a detectable cold spot on our maps of the primordial sky. It is a direct and elegant link, a chain of causality connecting a vast modern-day structure of nothingness to a faint, cold fingerprint on the first light of creation. This emptiness is not a distant abstraction. It is our next-door neighbor, an immense cosmic desert called the local void that presses directly against our galactic street. Picture the local sheet, our flat plane of galaxies, as a floating island. On one side of this island, we feel the gravitational pull of the Virgo cluster and the Great Attractor drawing us inward. But on the other side, there is a profound and opposite force, a push. The local void is a region of exceptionally low density, spanning nearly 200 million light-years. Because it contains so little matter, its gravitational pull is significantly weaker than that of the surrounding cosmic structures. This creates a gravitational imbalance. Think of it like being in a boat on a pond where one side of the pond is suddenly drained of water. The boat will naturally drift away from the empty side, pushed by the higher water level on the opposite shore. In the same way, our entire local group of galaxies is being gently pushed away from the local void and toward the denser, more massive regions of our local universe. This subtle but relentless pressure is a fundamental part of our cosmic motion, a contributing force to our 2 million km/h journey toward the hidden Great Attractor. We are not just being pulled, we are also being actively shoved by the nothingness next door, a constant reminder that even emptiness holds a tangible power in the grand architecture of the cosmos. The brilliant galaxies we admire are merely the glittering lights on a mountain of shadow. If we could place an entire supercluster on a cosmic scale, we would find a shocking truth. The stars, the glowing gas, the planets, everything we consider to be the universe of light, accounts for a paltry few percent of the total mass. The overwhelming bulk, over 90% of the substance in these titanic structures, is dark matter. This is the fundamental architecture of reality. What we see is not what is truly there. The galaxies are like a thin layer of glowing moss growing on the surface of a colossal, invisible mountain range. They simply trace the contours of a landscape we cannot see directly. This is why gravitational lensing is so crucial. When we observe the way a supercluster bends the light from galaxies behind it, we are weighing the entire mountain, not just the moss. The sheer amount of gravity required to create that distortion far exceeds what all the visible matter could possibly provide. The majestic walls and filaments of the cosmic web are, in their essence, sculptures made of shadow, with the luminous universe serving only as a faint and fleeting decoration. This means the largest things in existence are composed of a substance whose nature remains one of physics' greatest mysteries, a silent giant holding the stars in place. This foundational rule of cosmology is now under direct assault. The cosmological principle has been a guiding light for centuries, a simple but profound assumption that the universe is both homogeneous and isotropic. In plain terms, this means that if you zoom out far enough, the cosmos should look roughly the same in every direction, a smooth and featureless sea of galaxies. The principle defines what sufficiently large means, a scale beyond which no new giants should emerge. This is not just an academic idea, it is the bedrock upon which our entire understanding of the Big Bang and cosmic evolution is built. Yet the existence of titans like the Hercules Corona Borealis Great Wall, a structure nearly 10 billion light-years across, drives a stake right through the heart of this principle. How can the universe be considered smooth and uniform when a single object spans a significant fraction of its entire observable volume? This wall is not just large. It exists on a scale that was supposed to be the very definition of smoothness. The principle's idea of sufficiently large is shattered, forced to a scale so vast it might not even exist within our observable horizon. We are left staring at a cosmos that appears fundamentally lumpy, a place where the largest structures we can see challenge the very definition of an orderly universe. This is not a minor puzzle, it is a crisis for cosmology. Either these colossi are statistical flukes, fantastically rare anomalies that we just happen to find, or our most basic assumption about the universe's structure is wrong. If the cosmological principle fails, we must ask what profound new physics could possibly explain a universe that prefers to build on such an impossibly grand scale. This repetitive pattern of clusters within clusters reveals a universe that builds upon a single, elegant blueprint. From the smallest galactic gatherings to the largest walls, the cosmos exhibits a striking property known as self-similarity. It is a pattern that echoes itself across vastly different scales, much like a natural fractal. A tiny fern frond, when examined closely, mirrors the branching shape of the entire fern plant. A jagged coastline, viewed from space or from a pebble on the shore, shows similar levels of intricate detail. The universe operates on this same profound principle. Our own local group of galaxies is a small cluster. It is embedded within the local sheet, a larger flat arrangement. That sheet is a part of the immense Laniakea supercluster, which itself is just one strand in the sprawling Pisces-Cetus supercluster complex. Each time we think we have found the largest structure, we zoom out to find it is merely a component of something even grander. This cosmic nesting doll seems to have no end, a fractal reality woven into the fabric of space itself. Yet the universe is not a perfect mathematical fractal. At a certain immense scale, the pattern is theorized to finally smooth out, reaching the fabled end of greatness. But our continued discovery of colossal walls and complexes challenges that very limit, suggesting the fractal-like nature of the cosmic web might extend further than we ever thought possible. What does this profound self-similarity tell us about the fundamental forces that shaped everything from the first instant? It hints at a cosmos where simple rules, applied over and over again through gravity and expansion, can generate an infinity of complex and beautiful forms. Deep within the heart of a galaxy cluster, a silent, violent feast is taking place. The brilliant cities of light we have explored are not always peaceful metropolises. In their dense downtown cores, a process of cosmic consumption unfolds, known to astronomers as galactic cannibalism. The dominant player in this drama is a specific type of galaxy called a CD galaxy, a supergiant elliptical that sits at the very gravitational center of the cluster. Think of it as the city's central castle, an immense fortress whose gravitational pull commands the entire region. Over billions of years, this central giant grows not by creating new stars from within, but by devouring its smaller neighbors. As satellite galaxies swing too close on their orbital paths, the immense tidal forces from the CD galaxy begin to stretch and pull them apart. A smaller spiral galaxy, with its elegant arms of stars and gas, does not simply crash into the giant. Instead, it is slowly, methodically shredded. Its stars are stripped away, drawn into the vast halo of the cannibal, while its gas is siphoned off, fueling new bursts of star formation or feeding the supermassive black hole at the giant's core. This is how the most massive galaxies in the entire universe are assembled. They are not born that way. They are built over cosmic time through a relentless diet of their galactic companions, growing to sizes that would be impossible through star formation alone. This violent process leaves behind ghostly evidence. Vast, faint streams of stars, the stellar debris of long-digested galaxies, can be seen surrounding these central giants. the fading echoes of ancient meals that built the titans at the center of the cosmic web. Our cosmic maps are about to be rewritten by a new generation of eyes in the sky. The James Webb Space Telescope is not merely looking at distant galaxies, it is conducting a form of cosmic archaeology, peering back to an era known as the epoch of reionization. This was when the universe was a dark, featureless expanse of hydrogen gas, and the very first stars and galaxies were just beginning to ignite. Webb is searching for the faint, reddish smudges of these infant galaxies, not as isolated points of light but as a pattern. By plotting their positions across the deep sky, astronomers are tracing the very first threads of the cosmic web as they were just beginning to glow. We are witnessing the web's construction in its earliest stages, seeing how gravity first began to pull matter into those primordial filaments from which everything else would grow. But to understand the web in its modern, mature form, we need a telescope of a different kind. The upcoming Nancy Grace Roman Space Telescope will be a survey machine of unprecedented power. Imagine a telescope with a field of view 100 times larger than the Hubble Space Telescopes. This allows it to perform a cosmic census on a staggering scale, mapping the positions and distances of millions of galaxies with incredible speed and precision. This vast, three-dimensional map will chart the cosmic web in finer detail than ever before, revealing the subtle ways dark energy has been stretching its filaments and expanding its voids over billions of years. The synergy between these two observatories is what promises a revolution. Webb shows us the blueprint of the web in its infancy, and Roman will show us how that blueprint was executed and warped by time and dark energy. Together, they will push our vision to new limits, almost certainly revealing structures of such immense scale and strangeness that they will challenge everything we think we know about the universe's architecture. Even the universe's first light holds a disturbing secret. Woven into the faint glow of the cosmic microwave background is a pattern so peculiar that astronomers have named it the axis of evil. This is not a single structure, but a bizarre large-scale alignment, a preferred direction in the cosmos that should not exist. The cold spots and hot spots in that ancient baby picture of the universe, the fossilized ripples from the Big Bang, appear to be subtly aligned with the plane of our own solar system and the direction we are moving through space. This is deeply unsettling. According to our most fundamental cosmological principle, the universe should have no preferred direction. It should be isotropic, looking the same in every direction, with no up, down, left, or right on the grandest scales. The axis of evil suggests a cosmic spine, a fundamental skew in the fabric of reality that orients everything from the smallest planets to the largest walls of galaxies. This alignment does not stop with the microwave background. The spin axes of vast numbers of spiral galaxies and even the distribution of distant quasars seem to hint at this same mysterious preferential direction. It is as if the entire observable universe has a subtle grain, like a piece of cosmic wood, and everything within it is aligned along that grain. The probability of this happening by random chance is astronomically low. So we are left with two deeply uncomfortable possibilities. Either this is a colossal, one-in-a-million fluke of our particular vantage point, a statistical mirage that will vanish with better data, or it is real. If it is real, then the axis of evil is not just an anomaly. It is a direct challenge to the core of modern cosmology, forcing us to question if the universe itself has a fundamental architecture we have been completely blind to, a hidden axis around which all of creation turns. Every photograph of the distant cosmos is a page from an ancient history book. When our telescopes capture the light from a galaxy cluster 5 billion light-years away, we are not seeing it as it is today. We are witnessing a moment frozen 5 billion years in the past, a time when our own solar system was just beginning to form. This is the ultimate magic of astronomy. Because light takes time to travel the immense voids of space, the farther out we look, the deeper back in time we see. By meticulously mapping these colossal structures at varying distances, we are not creating a single snapshot. We are assembling the frames of a cosmic movie, a film that spans the entire age of the universe. We can watch a protocluster in its chaotic infancy, then find a similar structure a little closer and see it as a more mature city, and finally observe a nearby cluster in its final, settled form. This allows us to trace the entire life cycle of the cosmic web, from its first faint threads of dark matter to the brilliant, sprawling metropolises we see in the modern era. We see the voids expanding and the filaments thinning under the influence of dark energy, not as a theory, but as a recorded history written in the positions of billions of galaxies. This grand chronological map is our only way to understand how the universe built itself, revealing the dynamic story of the largest structures in existence, a story still unfolding across the deepest reaches of time and space. The vast voids between galaxies are not quite as empty as they seem. They are filled with a ghostly presence, a faint, superheated fog known as the warm-hot intergalactic medium. This is the WIM, a tenuous gas scattered along the invisible filaments of the cosmic web, heated to temperatures of millions of degrees. Because it is so incredibly diffuse and so blisteringly hot, it does not glow in visible light. Instead, it betrays its presence only by the faintest absorption of ultraviolet light from distant quasars, or as a wispy, X-ray shimmer against the darkest patches of space. For decades, astronomers faced a cosmic accounting problem. When they tallied up all the normal matter, the baryons that make up stars, planets, and us, a huge portion was simply missing. The universe's books did not balance. The WIM is the solution to that mystery. This elusive hot gas is thought to contain the final third of the universe's missing normal matter. It is the hidden reservoir, the cosmic humidity that clings to the web's dark scaffolding. So the grand architecture we have explored is not just a skeleton of dark matter dotted with glittering cities. It is also a plenum, a universe filled with an invisible, searing ocean, completing the inventory of everything we are made of and tying the entire cosmic structure together with threads of million-degree gas. These immense structures, from the smallest filament to the largest wall, are the ultimate historical record. Their very existence and the precise statistical patterns they form point back to a singular, explosive event in the universe's very first moments. This was the inflationary epoch, a period of exponential expansion so violent it makes the Big Bang itself seem slow. In less than a trillionth of a second, the universe ballooned from a subatomic speck to something far larger than our entire observable cosmos today. But inflation did more than just stretch space. It also stretched the very fabric of reality at the quantum level. At those unimaginable scales, empty space is not truly empty. It is a seething, bubbling foam where particles and energy flicker in and out of existence. These are quantum fluctuations, momentary ripples in the energy of the void. Inflation took these tiny, random quantum jitters and magnified them to cosmic proportions, stretching them from the microscopic to the macroscopic and imprinting them as minute differences in density across the entire infant universe. Those amplified ripples became the gravitational seeds, the tiny imperfections that gravity would spend the next 13.8 billion years working on. Every filament, every void, every great wall is a direct descendant of a quantum fluctuation from the first instant of time. The cosmic web is not random. It is a fossil, the magnified echo of the universe's first quantum whisper, a pattern written in the language of the very small and stretched across the canvas of the very large. This journey has taken us from our own galactic doorstep to the very edge of the observable universe, a mind-boggling voyage across billions of light years. We have navigated the immense Laniakea supercluster, stood in awe before walls of galaxies spanning over 1 billion light years, and peered into voids of profound emptiness. Each discovery has been a step in a grander revelation that the cosmos is not a static collection of lights, but a dynamic, evolving tapestry. These colossal structures do more than just defy our sense of scale. They actively challenge the very foundations of our theories, from the cosmological principle to the predicted end of greatness, forcing us to rewrite our understanding of cosmic history. The universe is not a finished sculpture, but a living, breathing construction site, constantly being reshaped by the invisible hands of dark matter and dark energy. The next time you look up at the night sky, remember you are not just looking at stars, but at the glittering nodes of the largest construction project in existence, the cosmic web. We have covered 50 staggering facts, but the universe always holds more. Which of these cosmic giants left you the most astonished? Share your mind-blown moment in the comments below, and subscribe to continue exploring the universe's greatest mysteries together.